3D rigid body equilibrium, but we're going to focus on solving the problems now. So drawing the FBDs and solving these problems. So our learning objectives, we need to be able to identify all the rigid objects and which are two force members. We've talked about that same idea in 2D. That's going to be our list of possible FBDs, which is our next learning objective, is then to identify the correct FBD to solve for those specific support reactions or geometry. We have 6 equations of equilibrium, and we need to identify which equation we should be used first, second, third, etc. And that's really going to help us out with solving that problem. These learning objectives are really the steps that we need in order to solve these problems. So not only, like we talked about before with our learning objectives for this class, are they like exam questions and very much related to the exams and what we need to know, but a lot of times they provide for us the steps that we need to take to solve these problems. The first homework problem you have on this topic is a bar supported by a thrust bearing A. So we see that thrust bearing, we should know what forces and moments go there, and this cable from B to C. A thrust bearing A is going to have forces in all 3 directions because it's a thrust bearing. It can also have a moment about the x-axis and a moment about the z-axis. Now, last time we talked about there are times when we don't include those moments. Remember, the easiest way to do that is count the number of unknowns. This one, including the moments on there, including M, we have 6 unknowns. So we're going to leave the moments on there because there's 6 of them. And so we'll put the moments on that FBD. Now, this one here, problem number 2, it's a tutorial just pointing out it's not in the back of the book. This problem is in the back of the book, so you could look at the book for the numbers from the book and also see in the back of the book what the correct answers are for those numbers in the book. This one, though, tells us that there's no force in the x direction, and it's because it's a single journal bearing with a square shaft. So a journal bearing, remember, does not have a force along the length of the shaft, so there's no AX when we're drawing that FBD. This one as well, take a look at what other reactions would occur at that square shaft there. Okay, and then our third problem is a door with these 2 hinges. There's a hinge at A, a hinge at B. They're asking us to find the reactions at those 2 hinges. Okay, here's the example that we're going to do today. So we have a 3D system right here, a pipe assembly that supports the vertical load shown. And it's asking us to determine the components of the reaction at the ball and socket joint A and the tension in the supporting cables BC and B to D. So let's go ahead and let's start by just drawing our given information. And like we've done in the past, when we have 3 dimensions, 3-dimensional problems, instead of trying to draw all of our dimension lines and show those dimensions, what if we just drew a general picture and labeled the coordinates for those points? That's going to help us when we're starting to solve the problem, and it's also going to be easier to draw the picture. So they show the y-axis kind of at a little bit of an angle here. I'm going to go ahead and just draw the y-axis straight to the right. They have the z-axis coming straight up, and then the x-axis is coming out of the page there. And our pipe assembly looks like this. It kind of starts here, and it comes up like that, and then it makes a straight line out parallel to the y-axis right there. And then we have a cable that goes from this point B right here, and I'm just going to show in general, right? I'm going to show, oh, there's a cable that goes to about right there. And then there's another cable that goes to about right there. And I'm not super worried about getting those in exactly the right spot because we can just label all of our points here. Point A is a ball and socket. And so if we have a ball and socket, we should be able to think about what is that allowing to happen? What is that preventing from happening, to figure out what forces and moments are going to go at that ball and socket. We've got a couple of forces out here. We've got a 3 kilonewton force that's about right there. And then we've got another force out here of 4 kilonewtons right there. Let's label our points here. Let's see, we have A is the ball and socket. B is that point right there. C is this point over here. D is that point there. And let's label our locations of our two forces. How about we got A, B, C, D. Why don't we make it E and F out there? Okay, now we haven't done the coordinates yet, but why don't we go ahead and let's list all those out. So point A, I'll do that one. That's easy. 0, 0, 0. So I took care of the easy one. How about the x coordinate of point B? Basil, what do you think? What's the x coordinate of point B?
0.
0. Okay, well, I've got you on the line here. How about the y and the z too?
1 is z and y is 1.
Y is 1 too. Yes, excellent. Thank you. Okay, so we got point B. How about the coordinates for point C here? Chris, Como.
That'd be 2, 0, 3.
2 in the x, 0 in the y, and a positive 3 in the z direction. Absolutely, thank you. Point D here is actually almost the same as point C, except we have a -2, a 0, and then a 3. And then how about point E as well? So point E has coordinates in the x direction, it's going to be 0. In the y direction, it's going to be, we're going to go 1, and then another 1.5, and that puts us up to right there. And then we go another 1.5. So it's actually 1.5 plus 1.5 plus 1, so 4. And then in the z direction, it's going to be 2. And then point F is going to be a 0, let's see, not 4. In the y direction, let's see, it's going to be 4, how about a 5.5, 5.5, and 2 in the z. And I guess these are all in meters. We could put meters on all of those to make sure we've got our units on there. Okay, so we've got all of our given information there. And what they're asking us to find for this problem, and I'll squeeze this at the bottom of our page there, is the reactions at A and the force in CB and DB, or we could call them BC and BD. Whatever. Doesn't matter what order we put those letters in. Okay, so our solution then, if we are trying to find support reactions, if we're doing equilibrium, what is the first thing that we need to do in our solution? What's our, go back to those learning objectives? Anyone? Yeah, identify, the two member forces, the FBD, right? It's really about the FBD. Now, in identifying our rigid objects, this one, and you'll see a lot of the problems, the homework problems that I showed you, they all really only had one rigid object that was not, right? This one technically has 3, right? We have the cable from B to C. We have the cable from B to D. We have the pipe assembly, A, B, E to F. But there's really only one rigid object for this problem, and that was going to be that. So we'll do an FBD of this A, B, E to F. And if we really wanted to go through our process and consider B to C and B to D as rigid objects and whether or not we should do an FBD of those, they don't have any known values. And so we would not, we really don't need to look at those anyways. And actually, we don't usually draw FBDs of two force members because they don't have any known values on them. So yeah, let's start with our FBD. And I'm just going to draw in general here. We have our, I guess I should use the same colors. Let me use blue for our pipe assembly. So we have our pipe assembly that basically looks like this. And I just want to describe all the unknowns that are going to be on here. Like we have our 3 kilonewton, that's right there. We have our 4 kilonewton, that's right there. Now at A, what does a ball and socket allow? It allows rotation. It doesn't prohibit rotation. Does it allow translation though? No, it's not allowed to move in the X, the Y, or the Z. So let me draw this, and I'm just going to show an AX. We're going to have an AY, and then we're also going to have an AZ. And then in order to draw the FBD of that pipe assembly, we had to cut through those cables, didn't we? We had to, or remove those cables. And so we're going to have a tension in each of those cables. We'd have like a tension from B to C. And now that we're in 3D, we're going to describe that as a vector. And then we also have a tension from B to D over here as well. And the reason we're going to do those in vector format is because we can express that then as an unknown magnitude times the unit vector from B to D, because we know what direction that force is going in. We know the unit vector, which is telling us, right, what direction that force is going in. We just don't know the magnitude of that force, but we don't want to think about that TBD as like an unknown X component, an unknown Y component, an unknown Z component. We want to think about it as an unknown magnitude times the direction that it's going in. So TBC, same thing. We're going to say, I didn't give myself a lot of room here, but TBC times the unit vector from B to C right there. And of course we have all of our points here. This is point A, this is point B, this is point E, and this is point F out here. And we've described the location of all those with our coordinates that we listed under the given information. So, how many unknowns do we have at this point? Well, we've got AX, we've got AY, we've got AZ, we've got the magnitude of TBC and the magnitude of TBD. So we have 5 unknowns. We have 6 equations to solve for these, so we can certainly come up with enough equations to solve for those unknowns. But it's going to be really beneficial if we put together a roadmap. And so like this roadmap, I think about this like you're driving down like in some unknown place that you've never been before, and you're like, okay, well, I can look at my map, I can see what street I'm on, and I can see where I'm going. And so we're kind of in this unknown, right? We've never solved this problem before. And so if we set up a roadmap here, it's going to tell us like what street to turn on, or for our case, it's going to tell us what equation do we want to start with. And so our roadmap, let's just list out all of our possible options. If we did sum of forces in the X, if we did sum of forces in the Y, if we did sum of forces in the Z, and if we did the sum of the moment equations, our roadmap is really going to list out for each of our equations what unknowns do we have in that equation. So if we did sum of forces in the X here, what unknowns am I going to have in that equation? which things have, TBC and TBD, absolutely, because they have an X component. And how do we determine that we have an X component? And John, I see your question. I'll get to that in 1 second here. But TBC and TBD, how can we tell? Well, that's another benefit of writing down our coordinates. Like we know from B to C, does B and C have a different X coordinate? Yes. So they do. That is going to have a component in the X direction. So we can use our coordinates that we wrote down to figure out if those are going to have an X component, or we can look back in our picture and we can say, yes, I think there is an X component based on where B and C are located in our picture. And then let me finish this equation. I see Kaylee has suggested also that AX is going to be an unknown. So that's all of our unknowns in that sum of forces in the X equation. Now let me go to John's question. If it's a ball and socket, do we know that AX, AY, and AZ are all 0? No, because we know like this ball, right? That we basically have, right? This ball is in this socket, and so if I tried to move it this way, it wouldn't allow me to do that. So I can have a Y component, or if I tried to move it this way, it wouldn't allow me. The ball in that socket, the socket is preventing the ball from moving. What the socket allows, though, is it allows it to rotate. So we're not going to have, what we know we don't have is our MAX, our MAY, and our MAZ. There's not a reaction that's trying to prevent this from rotating, right? There's not like it's saying, oh, you can't rotate. No, it's allowed. That ball and socket allows it to rotate, so we don't have a moment. Does that make sense, John? Okay, any other questions? Okay, so right now, if we think about our roadmap, if we did sum of force in the X direction, we would have 3 unknowns. Is there any way to solve for 3 unknowns with 1 equation? No. So let's look at sum of forces in the Y. That would have a TBC, a TBD, and it would also have an AY. So we added, now we have 2 equations, but we have a total of 1, 2, 3, 4. We have 4 unknowns. So still no way to solve this. What I'm looking for, and we've talked about this before, is I'm looking for 1 equation with 1 unknown. If I can find 1 equation with 1 unknown, then that's great. I don't have to do any substitution or any extra algebra. If I can't find that, then I want 2 equations with 2 unknowns. If I can't find that, 3 equations, and so on. So let's move on to sum of forces in the Z. We'd have also a TBC and a TBD because those have a Z component, and an AZ in there. So now I've got 3 equations, but I have all 5 of my unknowns. And so there's no way I can manipulate 3 equations to give me 5 unknowns. So let's move on to our other options. And so this roadmap is really a list of all our options. And we've talked a lot about identifying all our options for statics, and that being a really good way to solve problems. And then once we identify those options, picking the best option. So what about if we sum moments here? And so that's our next option. So if we sum moments, we have to pick, we're going to do X, Y, Z, but we also have to pick a point. What point can we sum moments about and get rid of a lot of unknowns? Anyone? What point should we sum moments at? Yeah, point A. Because if we sum moments at point A, AX, AY, and AZ do not cause a moment about point A. So that means we got rid of all those unknowns from that equation. And then we'll look at, well, what if we do this on the x-axis? Well, if we sum moments on the x-axis, what are we going to have? And we can look and we can see, well, is TBC going to cause a moment about the x-axis? As long as it's not going through the x-axis, as long as the line of action isn't going through the x-axis, it is going to cause a moment. So TBC would cause a moment. TBD, if the line of action is not going through the x-axis, so it will also cause a moment. So TBD, those will be our only 2 unknowns in that equation. So now I've added an equation. It only has 2 unknowns in it. I can think about all 4 of my equations, and I have 5 unknowns, so I'm getting closer to having an equal number of equations and unknowns, but I still haven't really figured out where I want to start. How about moment about A and the y-axis? If we do it about the y-axis, again, we're also going to have TBC and TBD because they do not go through, the lines of action of those do not go through the y-axis. And if we go back to our original picture over here, we can see like this line of action would kind of go off this way. This line of action would come out away from the y-axis. And so those are going to show up in that equation. So now look at what we've done. Our roadmap, here's 2 equations with 2 unknowns. Now that's a lot better than just going, let me write out all 5 of my equations and start substituting. Now I know I can get 2 equations, 2 unknowns. I can solve for those 2 unknowns and then look at what happens once we get those 2 unknowns. Sum of forces in the x is only going to have 1 unknown. I can solve that for ax. Sum of forces in the y is only going to have an ay, and sum of forces in the z is only going to have an az. So we've gone from having like 5 equations and being like, oh my gosh, how are we going to solve all these 5 equations at the same time? To now we want to do these 2 equations. Okay, so now how do we do the sum of the moments about point A equal to 0? Well, we're going to sum the moment vectors about point A equal to 0, and that's going to be an r from A to B crossed with the tension from B to C, plus an r from A to B crossed with that tension from B to D, plus an r from A to E crossed with that minus 3k hat, that at E there, and then plus an r from A to F crossed with that minus 4 in the k hat direction. So we're going to have to do 4 cross products to get this done. So you could imagine these 4 cross products would be like us driving around in the dark in a brand new city or something and just, you know, being like, wait, what are we doing? Where are we trying to go? What street are we looking for? Well, we know we're trying to get the sum of moments about A in the x-axis, the sum of moments about A in the y-axis. Well, how do we get that out of that equation? We do that by grabbing the I component. That's going to be the x-axis. And we grab the j component. That's going to be the y-axis. So right now, though, let's write out all the vectors that we are going to need, like r from A to B, and you know we're going to need that vector, right? Well, we can look back at our coordinates back here. It's a little hard for me to see both of those, but we can look right from A to B. Isn't that going to be a 0 minus 0, a 1 minus 0, a 1 minus 0, just final minus initial? So I'm going to do a lot of the work here for us. So A to B is going to be a 0, 1, 1. R from A to E is another one that we're going to need. It's really nice and handy to have those coordinates written out because we can just look at those numbers. Remember, we're taking out multiple, we're not doing multiple steps at a time. We are just, we wrote out the coordinates of each point and we could focus on the X and then the Y and then the Z. And now we're not trying to do like the position vector and figure out the coordinates all at the same time. And then R from A to F is going to be a 0, a 5.5, and a 2 right there. Okay, and then I see a question here. Are the 2 applied forces 3 and 4,000 newtons, or is the K representing the Z direction? No, those are, good question. Yes, these are kilonewtons. So those are kilonewtons there is what we're talking about. But the reason I know they're going in the K direction is because of our original information, right? The 4 kilonewton and 3 kilonewton are going in the negative Z direction from our picture. So good question. Yeah, the K hat is different than the kilonewtons there. Okay, and then the other thing I want to write out here is the our TBC and TBD. And actually these are going to come in really handy. And so we can find TBC is going to be equal to the magnitude of BC times the unit vector from B to C. Well, we found the unit vector a bunch of different times, so I'm just going to go ahead and give us this information here. It's a 2/3 TBC in the I minus a 1/3 TBC in the J and a plus 2/3 TBC in the K direction. We can do the same thing for TBD. It's the magnitude of BD times the unit vector from B to D. So I didn't show explicitly us finding the unit vector from B to C and B to D, but the components are there, right? They're the 2/3 minus 1/3 and the 2/3. For B to D, it's a minus 2/3 times TBD in the I minus a 1/3 TBD in the J and a plus 2/3 TBD in the K direction. And just like writing out the coordinates at the very beginning of this problem, writing out these vectors is going to be super helpful for a step later in this problem. So I'm going to put a purple box around those so we can come back and find those. Okay, so now we have all the vectors that we need for all of these cross products here. We've got 4 different cross products that we need to go through. And so again, we're doing some of the moments about the vector A is equal to 0 is really what we're trying to do. And so like our first one, we've got an I, a J, and a K goes across our top row. And then RAB we know is a 0, 1, 1. So I'm doing the first cross product. I'm doing RAB cross with TBC. And then TBC, well, that's our 2/3 TBC, a minus 1/3 TBC, and a 2/3 TBC. And so we put the lines across there to say, hey, we're doing the determinant of that 3x3 matrix. That's going to tell us the moment that TBC is causing about point A in the I, J, and K direction. Now we're also going to have the RAB cross TBD. So we'll have an I, a J, and a K across the top. RAB, so we're still using RAB, so still a 0, 1, 1. And then we're going to have a minus 2/3 TBD, a minus 1/3 TBD, and a 2/3 TBD. There's our second cross product. Our third cross product here is going to be the RAE cross with our minus 3K. So minus 3K hat. So we have our I, J, and K. And then let's see, we're using R from A to E. That's a 0, 4, 2. And then a 0, 0, minus 3. And our fourth cross product here, which is going to be RAF crossed with that 4 in the K hat direction. So 0, 5.5, and 2, a 0, 0, minus 4. And we're really saying, well, all this has to be equal to 0 because we know that for equilibrium, the moment about the x-axis, the y-axis, and the z-axis has to be equal to 0. So out of these 4 cross products, though, look at that. We have 2 unknowns, don't we? So if we do these cross products, what we're going to find from that first one, we're going to get a TBC in the I plus a 2/3 TBC in the J minus a 2/3 TBC in the K direction. That's from the first determinant. Audrey wants to know how much time we should plan to spend on a question like this for an exam. Probably like an hour and 25 minutes, and then like just guess the rest of them. No, Audrey, good question. And actually, that brings up a good point, because I did want to talk about your all's feedback, and so I got the feedback earlier this week for those mid-semester where they asked for positive feedback. There's a lot of positive things. I'll definitely keep doing those things, and then also some things to improve. And a couple of those were relating to the exams and the studying for the exams and the time that it takes on the exams. And then the other challenges I think you all are having are the homework, and particularly the handwritten homework. Let me talk about the handwritten homework for a second here first. If you're spending a lot of time on the handwritten homework, let's find a way not to do that. Technically, for the handwritten homework, if you get to this part right here, solution, you're done. And if you just if you just want to write your FBD, that's fine. That's all you have to do. If you just want to write the answer you get, that's all you have to do for the handwritten homework. Okay, so you could even copy the pictures off of Mastering Engineering, so you don't have to draw the given information, write a sentence on what it has to find, put something in your solution, and you're done. Now, that's not the intent. The intent is to improve your problem solving skills, to help you when you don't get the correct answer on Mastering Engineering, etc. Right? For the exams, yes, the exams are tight, right? It's a time crunch. Now we do, it's intentional that we have questions that take longer and questions that are shorter. I would not put something like this on an exam. I might ask you to pick the cross products. List out all the cross products, or tell me where should you take a moment about, or something like that. But in terms of for the exams, I think there's enough time if you're not trying to figure out how to solve the problems. And so what I recommend doing is for those exams, and you practice the supplementary example problems are really good. Take a look at my study guide approach as well. That is up on Canvas. It's at the very top of where I post all my lecture recordings. It's highlighted up there. It says study guide approach. Take a look at that for more problems to study from. And then come up with a way where you can look at a problem and you can say, oh, I would do R cross F and I would solve for TBC and TBD. Okay, so yeah, don't expect to have a problem like this on an exam. So thank you for asking that, Audrey. And we can continue talking about that. I'm happy to talk about that more in office hours. And we can actually that's probably the best place is in office hours. Or if you can't make my office hours, do send me an email, and we can find a time to meet outside of those office hours. Okay, so this was our first cross product here. This was our RAB cross with TBC. That was from that run right there. And then if we move on here, we're going to have a plus TBD in the I minus a 2/3 TBD in the J and a plus 2/3 TBD in the K direction there. And so that one is that's our RAB cross T from B to D. So that would be from this determinant up here. And so I'm doing all the math for us. And then the last two, note the last two determinant, the last two 3x3 matrices there, they don't have any unknowns. And so what we're going to find out of those is a minus 22i and a minus 12i. And so we know all this has to be equal to 0. Now, we have identified earlier in our roadmap, right? What are we doing? We did all these cross products, but yeah, what are we doing? Oh yeah, we want to do sum of moments about a in the x and sum of moments about a in the y. Well, take a look at these, at our vectors here, the most recent thing we wrote down. If we just grab all the I stuff, there's sum of moment about a on the x-axis. If we grab all that stuff. Or if we grab all this stuff right here, if we just grab all our j components, there's sum of the moments about a on the y-axis. So we can, at this point in time, we've really done a lot of the work here. And so for summing moments about a on the x-axis equal to 0, it's going to be TBC plus TBD minus 34 is equal to 0. Look at that, all that work, and we came out with this nice, like linear equation that I think is going to be pretty easy to solve. Actually, can anybody tell me at this point in time what the magnitudes of TBC and TBD are equal to, even before we do sum of moments in the y? Anybody tell me? Somebody out there? Yeah, it's 17. Absolutely. And Leah, how did you know it was 17?
Well, the equal forces, since they're both equal distance from B, so they should be the same.
Yeah, absolutely. If we go back to here, don't we have symmetry? We have symmetry on the YZ plane. And so Leah noticed that, oh, well, C is the same distance and D is the same distance away from that YZ plane. So they're balanced. Along that YZ plane, we have symmetry. And so she said, well, they have to be equal to each other. Well, that we can always use symmetry. It's fine, but it never replaces one of our equations, or it never adds to our equations. Look at what sum of moments about the y-axis, which is on our plane of symmetry, and that was the next equation that we identified, 2/3 TBC minus 2/3 TBD, and that's all the j components, has to be equal to 0, so we can see TBC is equal to TBD. So we can identify symmetry, but it never, there's always an equation that'll tell us about that. And it's the equations that are on that plane of symmetry.
And then
talk about moment about the z-axis, but look at what moment about the z-axis would do. It would tell us also that TBC was equal to TBD. Look at the k components right here. Right? Those k, I don't want to do it in red. I don't want to like emphasize this or anything because we're not using it. But yeah, these ones right here, the k components, they would also tell us that TBC is equal to TBD. So now we know, well, TBC is equal to 17 kilonewtons. TBD is equal to 17 kilonewtons. And going back to our roadmap here, I'll come back to that in a second. I'm going to grab some stuff from our roadmap here. What did we say next? Well, next we can do force in the x, y, and z, and our only unknowns are going to be ax, ay, and az. And we had highlighted this stuff right here in purple because it's going to be useful later. Well, this now is when this is going to be useful. And the reason it's going to be useful is because all we have to do, just like when we did the moments, if we do sum of forces and the x is equal to 0, I'm just going to grab all the I components. Well, I've got 2/3 of TBC minus a 2/3 of TBD. And then I also will have a positive AX. And I grab the AX. This is, I found from the FBD right there. These, I just grabbed the I from our TBC and TBD. Actually, in this case, we're going to find that AX is equal to 0. So we drew AX on there. It's possible for it to occur, but because of that symmetry, AX ends up being equal to 0. Now we can move on and we can do some of the forces in the Y is equal to 0. Well, let's grab the J. So it's a minus 1/3 TBC minus a 1/3 TBD. Again, I'm grabbing the J's from these vectors that we had previously written. And then from the FBD, we're going to have a plus AY equal to 0. So we got to look back at our FBD, make sure we're not missing anything. We could solve, in this case, AY is going to be equal to 11.3 kilonewtons. And then we can also do sum of forces in the Z is equal to 0. And that's going to be a 2/3 TBC plus a 2/3 TBD. So again, I'm grabbing my K components there, plus an AZ. And then we can't forget about our -4 and our -3. So going back, got to look at that FBD to make sure we're capturing all the forces on there. And we would find that AZ is equal to a minus 15.7 kilonewtons. I want to point out here, just so we know about it, another way that we could have done this. Moment about an axis. If we did a moment about this axis right here, and we've done that before with the triple scalar product, that's an R cross F dotted with a unit vector. That axis from A to D, for example, would get rid of all of our unknowns except for TBC. So we can use the moment about an axis on these problems. There's no, the moment about an axis on your homework problems is not relevant. I just wanted to point it out that it's another approach. For example, on this problem, we could do moment about different axes, and it's a way to get rid of unknowns from our equation. All right, you're not going to see it on the homework, but I just wanted, we've talked about moment at axis before. I wanted to tie it in with what we just did. So